There is a distance between Thursday and Tuesday, and some of you may have forgotten where we stopped last time. And last time we started talking about tensors. And if you remember, we talked about tensor product. Here, the definition of the tensor product, which is also called outer product. And then at the very end, I showed you how the components of a tensor would look like. And this turns out to be a very important concept that I want you kind of to carry with you in your mind. Not that you memorize it, you just compare it to the vector component and just learn it. I don't want to call the word, I don't like to use the word memorize. Just have it in mind. So with that, we start today. First, I kind of finish up what I wanted to tell you about tensors. And then we will switch to talking about index notation. Now, from the survey in the beginning of the class, class number 1, it looks like that almost everyone, I think except for one person, can use a little bit of review, or it looks like tensor notation is something that most of you are not very comfortable with. Let's put it that way. So we start with that, and hopefully you become more comfortable. If you need more practice, or if you need to come to me, I'll be happy to help you more. Use these, I would say, weeks where you are not very busy with other things to kind of get very comfortable with that. So that's kind of what my plan for today is. So let's get started with an example on tensor components. So here is an example. So we start with an example. And this example kind of looks back at one example that we did before. Probably looked very, very simple to you. We introduced this, which I called at that time the vector valued function of a vector, I, for every vector which belongs to the vector space V. So, and we call this identity function. I use the word function, call this identity function. Very simple. So now I ask you this question: is this a tensor? Is I is a tensor? Why? Because I just didn't hear. Because it maps to a vector to a vector. Is that enough for I to be a tensor?
It should be also linear.
Exactly. I is a tensor because it's a linear mapping of vectors to vectors. Just that we all remember what we were doing. And now I want us to write down the components of I. So we all agree that I, in fact, is a tensor, because as Prabha pointed out, it's a linear function that maps vectors to vectors, and it's pretty simple. Now, look back at the definition of the component and see whether we can actually express the components of this vector. What did we say? What did we say before? It was just on the board before that you can write a tensor. Think about the vector. So tensor is just you add another dimension. So you have a summation over two indices from 1 to n, and then it's the component of this tensor. We all agreed this is a tensor, and then we have tensor product. So this one we read, if you remember, EI tensor EJ. That's one way to read this. So write down the component. I just give you a couple of minutes. Go back, see what was the formula for the component. See if you can actually write down the component for yourself. It's a good exercise. Just look back. What was on I can actually go back and show you. So you don't even. So this is. So the component of a tensor is a scalar value. It's just a component. It depends on the basis that you choose. So that's the definition. Just plug the definition of I in this definition and see what you get for the component of I. What I'm looking for is Ij, the component of tensor I.
You want us to write it out like a matrix?
No, I just want you to write the expression for Ij. It's a tensor. We're not talking about matrices.
Yeah.
Right? We actually talk about, today I'll tell you a little bit more about the connection between the two. But what I want you to write is this Tij I introduced you. Now try to write it for Ij. Just a tensor that you saw before. Excellent. Yeah, like that. What happens then? Try to
work it out.
Yeah. I want you to lose the fear of dealing with indices and tensors. They are not so scary. Yeah. So what happens then? What do we do after? It becomes very simple. Yes, that's a good start. Now, what else can you say? Yeah, that's a good start. So, I think all of you, I've seen almost everyone writing this, which I really wanted you to write once for yourself. I saw everyone writing that. I saw some people forgetting to put the notation for tensor. So this would be EI dot tensor I acting on tensor J. This is the definition. Now, what is function I? It takes every vector to itself. So what is this? It's just Ej, right? Some of you didn't go this far. And what is this product? Exactly, delta Ij. So we see that delta Ij is actually the component of the identity tensor with respect to the orthonormal basis. As simple as that. Okay. Now we want to look to see how would we formulate the component of the vector when a tensor is acting upon that vector. So next is, now that we are all warmed up, let's consider this tensor T, more general notation, acting on vector V. So I want to find the component of this product. That's kind of the idea. Well, what I can do is to write the tensor with the summation. You know how to do it, you can get started. And the vector with the summation in terms of the components, and then I work my way through that. So let's just do it. This is, I just substitute the tensor by the component, the summation. That you saw, it's the tensor product. And the vector we all know. I hope it's obvious to everyone that I cannot use I and j now again for vector. I have to choose something else. So now the rest is kind of simplifying this expression. I want to find out what would be the component. Before doing that, tell me what kind of object is TV. What am I looking for at the end? A vector, right? So I kind of bring everything together. Because v sub k, tij, they're a scalar, so I can move them freely. Something like that. Now, EI tensor EJ is a tensor acting upon EK. Look back in your notes in the previous lecture and see how did we define this vector product. See if you find something. So you have something written like A tensor B acting on C. This is how we define the outer product. And have that frame in your mind and try to see what this would be. Try to write it. So I write it quietly, meaning that I write it, you write it, and then you check to see whether what you have written matches what I have written. That's it? Perfect. So I can simplify this expression sorry about that. Oh, one more thing before I move. And we know what this is. You all told me before. So you agree with what you see here? Now I'm going to do something that may not be familiar to some of you, but we are going to actually to get into that later today. So don't worry if this looks not very intuitive for you. For some of you who have seen this before, what would be the Vk delta Jk?
VJ.
Exactly. But if you don't know why, or this is not very clear to you, don't worry about it. We are going to get to that. So for now, trust me that this is the case. So basically, here we eliminate k in a way. So we don't need it anymore. We don't need to sum over it. So I can just remove it from the summation. So I have just Tij Vj Ei. You probably can see where this is going. And you all told me that the outcome of this product is going to be a vector. And remember that I just put it here inside the cloud, that let's say a vector, you would want to write it in a form like this, right? So we are going in that direction. We have this E hat I, and then we have this summation. So to get there, I kind of have to separate the two summations with that in mind. So that's exactly what I'm going to do next. Let's see. So I'm taking the I one, I separate that, and because I want to arrive at the vector, and then I have Tij Vj here, and then this whole thing is multiplied by E hat I. So what would be the component of this product? It's nothing else but this sum, right? If you compare it to the orange cloud that I showed you. So the ith component of this tensor product, the action of tensor T on vector V would be simply this summation. So this is, let me spell it out. This is the ith component of the action of T onto vector V. So you see a form here which is going to come up very often. So you have a summation over an index which is repeated just twice. So you have Tij and then Vj. Have this in mind. This tends to be very important for index notation, what I'm going to tell you next. And before going a little bit further, in 3D, we are interested a lot of times in second order tensors. So we are interested in tensors which have this kind of components, and then I and j are basically going from 1 to 3. So how many components does a tensor like that have? 9. We all know that. So it turns out that if you arrange those components in a matrix form, you will have some sort of the tensor in the matrix form. So the second order tensors, they have a corresponding matrix representation. This doesn't mean that matrices and tensors are the same. It's just that the second order tensors, you can take the components, arrange them in a matrix format, and that would be the kind of matrix representation of the tensor. So sometimes we show that using this. When I write that, that means that I've taken all these components and I've arranged them 3 by 3, and then I have this familiar looking matrix that you all have seen, but this is not this tensor, it's the matrix representation. So some people like to think about scalars as the 0th order tensors, vectors as the 1st order tensors, matrices as the 2nd order tensors, and so forth. But you may just think about tensors and you think about those as the representation if you take the components and arrange them in a vector format or a matrix format. Is this clear to everyone pretty much? Okay, so I guess we can move then. Any questions actually? Okay, so we can move to a couple of other things about tensors that I want to tell you before moving to index notation. And one important thing is the transpose. Transpose of a tensor. So what is the what? I didn't intend to do that. Ooh. Okay, I got everything back. What is the transpose of a matrix? How do we transpose a matrix?
Row to column. Changing the rows to column.
Exactly, you take the rows and you arrange them in columns, right? So it turns out that there is a more general definition for transpose. So let's just go through that quickly. So consider this product. You have vector A dot tensor T acting on vector B. So there exists a unique tensor which we call, that's kind of the transpose, so I tell you beforehand, T such that for all A and B in B, you have this property. So A dot T acting on B would be equal to T acting on A dot B. So you are kind of swapping the action of T on vector A and B. So when you transpose, you are basically sweeping this vector from A to B. Now, let's find out what are the components of this tensor. That's a good exercise. So if you want to write a tensor, try to write this summation again for yourself. And if I want to look at an individual component, what do? I use this formula that I told you is super important. So again, This is the dot product of EI transpose acting on EJ. Somewhat try to remember this, however you know. And now try to look at the definition of the transpose, this general definition that I gave you up there. And now we want to swap EI and EJ, basically. How do we do this? So since this is the transpose, based on this definition, I can actually swap A and B, right? So I can write this as the action on EI dot EJ, just from the definition. And does this look familiar? What is this? No. The product up there is not equal to 100. You cannot take that parenthesis off. What is it? I heard something correct. It is JI, right? Remember, if we had like EI dot TEJ, now it is EJ dot TEI. This is a dot product. You can take the EJ and bring it to the other side. So I basically, from a somewhat unfamiliar definition, I actually got something that should look familiar to you. If I had asked you before, if you go for a matrix, from a matrix to transpose, you would all tell me like IJ, JI, right? So I started with a more formal definition, but at the end, we basically ended up saying that, I should write this correctly actually. Same here. That basically you are sweeping the indices. Okay. A few more things about tensors. Any questions about this so far? The next thing is the trace of a tensor. Let me put in parentheses. So here I don't give you a general definition. I give you just what we need in this class. And what is the trace of a tensor? Does anyone remember?
Tensor matrix sum of tensor.
Exactly. So for tensors, it's pretty much the same. Now you can say that. I write it down. You can say that. So basically, what your friend said, sum of the components on the diagonal, that means when I and j are equal. So that's why I don't have to write I and j, I just can write I equal to j, so I have just one summation. This is only true if we are defining the components with respect to an orthonormal basis. And since in this class this is what we are always using, we are safe. But I like to write this down because this is not the general definition. So this is good if the components of T are relative to an orthonormal basis. Okay? And if we have this assumption, if I want to define the determinant of a tensor, if I have used an orthonormal basis, again I emphasize that, then I can just define it as the determinant of the tensor that I would build by arranging the components of the tensor. So we know how to calculate the determinant of a square matrix. So if you take the components of the tensor and you arrange them in a matrix format, and you want to calculate the determinant of the tensor is the same as the determinant of that matrix. And that's what that sentence is telling us. And one last thing is, by the way, it looks like it's useful for some of you to look to see what the definition of determinant is, based on the introductory survey that I did. So just look it up, see how you would calculate the determinant. This we are not going to use a lot, but it shows up in some theorems, in the general form of some theorems. So I just write it in the form that, again, is relevant to this class. So here, instead of one dot, we use two dots. And it's actually very similar to the inner product of vectors. It's kind of what you would expect. So instead of AI bj, you basically have AI bi, you basically have Aij bij. What would be the output of this operation? It's a scalar. Okay. This is everything I wanted to tell you about tensors. So now let's move to index notation. So we kind of start index notation. And something which is called Einstein convention. Or Einstein summation convention, maybe would be better. So this is very important for the rest of this class. So if you are not familiar with, or if you have never seen it before, just please pay close attention. It's very simple, but you just have to learn it. So let's just start by looking at the definition of vector. So remember that how we would define a vector. We always use this summation, and then we have the component ui, and we typically use orthonormal basis. So we have an orthonormal basis, and it looks like that. So these are components of U, remember that the components, they are unique with respect to the chosen bases. So we always have to say relative to which bases? Relative to the selected bases. Last time we called this something like this. G and UI, they are unique. Once we have chosen the bases. I repeat that here. So if they are unique, so we can just use them to represent the vector. So instead of writing this summation, I can just use UI, and that would represent the vector. I don't have to write the whole summation. If I have an understanding of what bases we are talking about, I don't have to specify it. So when you are using this notation, UI can still mean the ith component of U. You have to look at the context. But it can also just mean the whole vector. So it can be still the ith component of U. You will have examples that you will see. But it can also mean just U. So summation convention or Einstein tells us that if you have this situation when you have a summation where you have an index which is repeated exactly twice, you can just simplify everything and you can just not show the summation sign. So the summation convention, we have this understanding that this is, if we write just UI, EI, we are actually doing this summation. But this index has to be repeated exactly twice. I write this. So if the index is repeating exactly twice, so could I write, would this be equal, did I take it brown? No. Okay. Could I use another symbol here? Yes. So this index is a dummy index. That's called the dummy index. It doesn't matter exactly what it is. You can also use something else. This means exactly the same thing. So now, what else I want to tell you here? So this is kind of one important definition. One thing which I want to emphasize here is that you cannot write, like if you see something like this, this is not allowed because this can be ambiguous. What does that mean? So this exactly twice is kind of an important aspect. So you are not allowed to have more than 2 repetition of the same index. So that's one thing. The other is that you can use whatever index. Doesn't have to be I or J, it can be anything. So with this in mind, when I write AI, BI, yes? Yes. If you have a summation, everything is okay. So it's not allowed without the sum. That's a good point. Thank you. You can, if you have summation, you can do whatever you like. But if you want to remove it, you can't, because then people would get confused. Now, AI, BI, what does it mean? Dot product. So can everyone see that? If it is the first time you see it, don't worry about it. It takes a couple of days. You have to just look at them a little bit, play with them. That's completely normal. And one way for yourself, if you want to make it easier for you, try to write the summation. Then it makes things easier. So we are working in a 3-dimensional space. So when you write that, you are basically writing something like this. And what does it say? You are basically taking a component of a vector, multiplying by the same component of another vector, and then you are summing the whole thing up. That's what you are doing. So then have this conversation with yourself, and then you convince yourself that this is dot product. If you have seen this before, this is automatic. So some of you may be very automatic, some of you not. Those who are automatic, I hope you don't feel very bored, but it's good that we go through everything. So another example, for example, let me move to the next page. It's becoming a little bit messy here. So in the beginning of the lecture, we looked at the components of the tensor. So if you have a tensor, I write it again because it's important. And Tij is the components. So am I allowed to take this summation sign off? Yeah, I can take it out. So if you want to use this shorthand convention, you just say, you don't need to why can I take it out? Because I have I and j, each one of them is repeated exactly twice, so I can easily take it out. It means, so that would be equivalent to saying that I have a tensor. I don't need to write the summation. You have said it, I have written this down again. So again, I and j are dummy indices. So I write it again one more time here. You can change them with whatever else that you like. These two things mean the same thing, as long as you keep the order and everything correctly. Okay. Another thing that you saw previously was I showed you using the summation. I wrote a lot of summation signs, and I kind of calculated what would be the component when one tensor is acting on a vector. And at the end, if you look back, I found out that the ith component of this action would be equal to the summation j going from 1 to n, and then you have the component of the tensor and the j component of the vector. Could I take this summation sign off? Why not? I'm sorry. That's a good point. J is repeated, but I isn't. But the summation is over J. So I can take the summation out. But this point is important. I can take the summation out because J is repeated only twice. So if I write this like that, it implies that I'm actually varying J from 1 to n, let's say 3, and I sum everything up. Now, that was a good point. Is it John, right? John? That he brought up. How about I? So J is called like the dummy index. In this case, I is called the free, or sometimes people call it distinct. I write both. And you can check that everything is okay if you look at both sides. On the right hand side, I have the dummy index, which somewhat eliminates itself because through summation. But I have one free index. How about on the left hand side? I also have one free index, so everything is okay. That's a vector. I don't even want you just to learn this. I want you to like it because it's cool, right? It makes things easier for us. I mean, if you can like such things, that's so. Now, this is something that we talked about a little bit earlier. I told you I'm going to get back to that. Let's look at delta. Let me write it the way I have written it before. Delta J I U I. Try to convince yourself that this is UJ. How would you do it?
With delta AI over 1 on its own, it's from 0 and I is a percent.
Exactly. So if another thing you can, I mean, this is exactly the case, but this is also implying this summation, right? So you are basically, when you see a repeated index, immediately you have to think summation. So if something is not clear for you, you can always resort back to the summation, and then it becomes clear until it becomes easy for you. So as Alex pointed out, because this is 1 or 0, now depending on the value of J, we don't know the value of J, but if J is equal to 1, we know that everything will be 0 other than delta 1, 1, and it takes out just U1. So this will be equal to U1. Everything else, all other terms in the summation will be 0. Correct? If J is equal to 2, so J is our free index. It can be anything. this is U2. And if j is equal to n, this is un. So you can see the correspondence between the index of u and this j. So this is equal to uj, basically. And this is a super important equation, like something that really you need to remember. So, and it's simple to remember because whenever you see the Kronecker delta, it kind of substitutes one index for the other. So sometimes it's also called the substitution operator, because it's kind of changing I to j. It comes in, it eliminates I and changes I to j, as you can see here. So this is super important. How about the trace? So we said that the trace of a tensor, if we choose an orthonormal basis, it would be the summation of the elements on the diagonal. Could we use tensor notation to write it? Yes, because you have I don't write the summation anymore. I is repeating twice. I just write it like that. Of course, I could have written it using some other index. Okay. Any questions so far? So another example is, I'm switching the colors somewhat. Oh, it's okay. The cross product. This is a little bit trickier. So the cross product of two vectors, what kind of object it is? A vector. To be able to write this in index notation, it turns out that we need to define one other symbol. So I write it and then I explain what it is. So there is a new symbol called, does anyone remember? Just to make sure you're all awake. Permutation symbol. If you haven't heard about it, don't worry. It's very simple, just has a fancy name. We need to have the permutation symbol, epsilon ijk, and then uj, so you leave I, and then you have ujvk. And what should I write on the left hand side? wi. So again, pay attention. You have j and k are dummy indices, but I is free. So on the other side, you also have to have a free. And this clearly, if someone sees that, they see that it's a vector, and one side and the other side has to be also a vector. So what is this permutation symbol for those of you who don't remember or have never seen it before? There is sometimes this is also called, we'll see it under this Levi-Civita symbol too. How many values does this have? So Kronecker delta just has 2 values, 0, 1. And permutation symbol, 3 exactly. How many values it can have actually? Total. When you have I, J, K in 3-dimensional space. 27, correct? So it is +1. I'm just making sure that everyone is awake. If this class, the timing is a little bit tricky, so I know that you all know. So if I, J, K form so-called an even permutation of 1, 2, 3. I'm going to explain in a moment what this is. -1 if this is an odd and this is otherwise. So an even permutation is, let's take 1. This is how I like to think about it. So 1, 2, 3, right? So even permutation permutations of 1, 2, 3 are what? One is 1, 2, 3. The other is, you start instead of 1, you start at 2. It is 2, 3, 1. So it's 1, 2, 3, 2, 3, 1, and the last one? Exactly. And the odd is kind of when you go to the other direction somewhat. You start from going to, you start looking at, that's how I so you have, what do we have? 3, 2, 1. Just follow the red arrows. 2, 1, 3. And then 1, 3, 2, right? And everything else is 0. So we have 27 values. How many are non-zero? 6. And the rest are 0. So that's the definition of, and going back, so that's how we define the cross product. You need to have that permutation. So this one I can write it and then ask you to work it out. How would you write this index notation? Before starting, tell me how many free indices do you expect to have? How many? If we have 1, exactly. If we have 1, that means that you have a vector. Remember, ui is the same as u. So if we know that this is a scalar, so it's 0. So try to write this down and see how it works. I write it, I mean, you guys have, I write it a little bit with more steps. Some of you have just written, so this is first the dot product, and then inside the dot product, then of course I can write this CJK, and remember that these are all kind of a scalar values, so I can move them around, and if I want to have something that looks nice and orderly. Okay. And as you can see on the right hand side, all the indices are dummy, so there is no free indices, so we are all good. This symbol is also very useful to define the terminal. So maybe I use another page. So let's define the determinant. As I said before, the determinant is defined as the determinant of the matrix that you make with the components of the tensor. So let the matrix A be, and I just talk about 3 by 3 because that's what we need in elasticity matrix. And basically Aij are the elements. At the intersection of the ith row and jth column, as you all know. So the determinant, this is the permutation symbol, and I, J, K. So this is what is called the row expansion. So you have the permutation and you have basically the 3 rows of the matrix. And you can also write it in this way, like a column expansion. Write this a little bit nicer. If this is very new to you, it's a good exercise to convince yourself of what I'm writing here. If there is a weekend and it's cold, you don't want to go out, you have nothing to do, just sit down and try to see whether you can prove some of these. You can actually write the determinant also in this form. Which I think it kind of looks very beautiful, like it's and you can see that you have a lot more terms here, so that's why it's actually, these are 6 determinants, so you have to divide it by 6 to get the determinant. And there are 2 important and useful properties related to permutation in the symbols, which I write down again. If you ever had some time where you really wanted to do something interesting, you can really convince yourself that these are the case. So one is, you can show that epsilon ijq, epsilon pqr is the determinant of a matrix full with Kronecker deltas. So this is how I know it. First I put the ijk and then the pqrs. And one thing which is very useful in a lot of derivations later on, probably not as much this, but a special case of this multiplication, where the first index is the same. So instead of having PQR, I have IPQ. So you have the same I on both. Like that. And this becomes very simple. Basically the just it has 2 terms, and see the way I remember this is JPKQ and then JQ and then KP. Yeah, JQ, KP. This you can very easily, from if you take the one above it as given, you can very easily get convince yourself that this is the case. How many free indices we have on either side in the last expression? 4. That's true. Okay. Let's put this in use in one example. So here, for vector quantities A, B, and C, see better, you can write, you can start from the left-hand side and get to the right-hand side. What is the nature of the object on either side of this expression? Have a better. So have this in mind. You can start with the I component of that expression. Should we finish this or should we leave it? Should I leave this to you to work on and then I'll start with that on Thursday? Should we finish it? Thursday? Thursday? So try to think about it before coming to the class on Thursday and write it down. So we'll start from here. Don't worry if it looks a little bit complicated. If you are seeing these things for the first time, that's completely normal. You get used to it.